Welcome to our 14th Fusion Friday. My name is Alex Alvarez.
My name is Brian Mongkolpoonsuk.
And we're application engineers here at KETIV Technology. So happy Friday, everyone. If this is your first Fusion Friday, welcome to you guys. Thank you for joining us and tuning in. Just a quick overview on what Fusion Fridays are, right? There are a series of webinars where we go over all the workspaces that Fusion 360 has to offer, as well as some of the updates that come or that Autodesk releases for Fusion 360, right? So as all you know, it is a cloud-based tool. So you don't have to wait for these yearly updates or these service
packs that the other traditional tools usually come with. So
right, yeah. So you usually get an update every 3 to 4 weeks, maybe 5 weeks, depending on what they have going on, and also depending on what people are saying about the tool, right? So that's one neat thing about Autodesk is that they really listen to their users, right?
Yeah, and we'll keep you guys updated with all these updates that Autodesk has.
Absolutely, yeah. That's what we do here at KETIV. So for today, we are going to be talking about thermal simulation, right? So again, simulation is really important for your products. You want to make sure that they are performing up to spec before you either release them out to market or before you do any live testing, right? So what better way to actually test your products inside the tool that you actually modeled it in, right? And then make all the changes that you're going to be doing inside that one single tool, right? So for today, Brian is going to be talking about thermal simulation, and hopefully you guys learn some valuable information today. So with that, I'll go ahead and pass it over to Brian and get the show going.
All right, thanks, Alex. So yeah, today we're just going to get straight to it. Our goal today is to validate our design using thermal and thermal stress simulation. We'll be testing a radiator, like you see on the screen here, as well as a brake rotor. So if you guys have any questions at all throughout this webinar, feel free to ask it, and we'll gladly address them at the end. So like I said, we're going to be first testing this rotor here, or this radiator here. And notice how, okay, you're in the modeling workspace. Let's just say we just finished creating this radiator here in the modeling workspace. Now, if you want to test it, we'll just hop over here to the simulation workspace. And now Fusion's prompting us and asking, okay, what kind of study you guys want to run? Yeah, we're going to choose thermal, but notice how we have 8 studies available to us. If you have the regular version of Fusion 360, you have access to the top 4. And if you have Fusion 360 Ultimate, you have access to all 8 of them.
Mm-hmm. Yeah, for those of you that don't know, you do have Nastran, the Nastran solver embedded inside of Fusion 360, right? So if you guys are familiar with Nastran, right, or Nastran NCAD, that solver is embedded inside of Fusion 360. So a really powerful tool that's performing these analysis for you.
Exactly, and the Nastran was used by NASA to take astronauts to the moon, to get you guys into perspective of how powerful the solver is. So now we're in the simulation workspace, and like every other workspace in Fusion 360, it has a left to right workflow. So just like reading a book, we're going to start here on the top left and move right. We already chose our study. Now we're going to go over to what is called Simplify. And this was, I think, released last year here into Fusion. Correct me if I'm wrong, but what Simplify does is it allows you to, like it says, simplify your model. So if you have like a huge assembly and you only want to focus on part of your assembly, you would go use this tool. And it temporarily reduces the complications, or how complicated your model is and what you're testing. And the benefits to that is that you'll have quicker solve times, and it'll allow you to focus more on what you're actually simulating here. So for example, if we want to only focus on the fins and the piping itself, we can go ahead and get rid of the water and fitting here by holding Control and selecting on it. And then we're going to go ahead and right click and remove those from our simulation. So this only temporarily removes it from our model here, but it doesn't actually like remove it or delete it from the actual model. And you can always go back to it down below here in the design history and undo that in the future if you want. So we'll go ahead and hit Finish Simplify, and now we're back in the simulation workspace minus those 2 components that I hid temporarily. All right, so now we're going to choose our material, which is next on the list here. And while we're modeling, our material was steel. However, we're going to want to change these all to aluminum. Let me go back and highlight these again. And now they're all changed to aluminum, and we're going to leave it as yield strength for the safety factor here. All right, so next on our list is we're going to apply some loads, some thermal loads to our model here, to our radiator. So we'll go ahead and hit thermal load. And the first type of load that we're going to apply is going to be applied temperature, which is going to be on the inside of the piping. And this is going to correlate with the temperature of the water going through the piping here. So first I'm going to go ahead and go to the browser and hide the fins because we're not going to need to select that at all. Then I'm going to strategically go to the right side of the piping here so I can easily select the insides of the pipe. So now if you notice, if I rotate to the side here, you can see that I selected where the water would be flowing through. And this is where the temperature is going to be applied. So I don't think in Kelvin. I'm going to go ahead and change the units to Celsius here. And we're going to make the water a little hot. We're going to make it 75 degrees Celsius. All right, so next we're going to focus on what the fins are doing here. And what the fins allows the radiator to do is to release heat by air flowing through it. So once again, we're going to choose thermal load, change the type of load to convection, and I'm going to select all the fins, all the faces of the fins, but then I'm going to deselect the inner sides of the fins where the piping is making contact with it. So notice how I strategically did a window select to unselect the ones on the inside, because there's no air flowing in between the connection of the pipe and the fins. Next, I'm going to change my convection value to 5 and 5 watts per meter squared Kelvin, and I'm going to leave my ambient temperature at that and move forward. And we have one more load that we need to apply, and that would be radiation. Now, radiation occurs whenever the value of, or whenever an object is greater than absolute zero, which is negative 450 degrees Fahrenheit. So if it's a little bit greater than that, it probably has a very tiny amount of radiation, but the more heat that it has, the more radiation that will occur. So we'll go ahead and choose radiation as our thermal load. Once again, I'll select the same surfaces as I did for convection and deselect the ones in the middle. And that's it for radiation. So we can check out the loads that we applied over here on the left-hand side.
We have a question here, Brian, too, asking how did we get the value of 5 for convection? So that's your convection coefficient, right? So that's something that you can look up in the table and get that value. So for this case, it was free convection, right, on a vertical plate. And then depending on the temperature that Brian had is the convection coefficient that he input for that table.
Right. Definitely do your homework, guys, on the loads that you're applying to your model here. The simulation is a great estimation of what the outcome is, but if you're applying loads and constraints in a way, or choosing a different material that doesn't really make sense, then then the simulation doesn't even matter, because you need to apply the correct loads and constraints and such. So be sure to double check on those before running simulations. All right, so now we applied our loads, we can go ahead and produce automatic contacts. And what automatic contacts is whatever components that I have, or solids that are within 0.1 millimeters of each other, they will be considered bonded. So I'll go ahead and generate that. And now it's going to read all the fins and the spacing between the fins and the piping. And now the contacts are good to go. we have a green check mark here on our clipboard, which is pre-checking our simulation status. And then we're going to go ahead and hit solve. Now, with the solving in Fusion, your simulation, you can either do it on the cloud, which takes cloud credits. And depending on how complicated your simulation is, it will correlate to the number of cloud credits that it costs. And you guys can check your own cloud credits by going to solve yourself in your simulation to see how many cloud credits you have. Some have 100, some have 20, some might not have any, depending on how you bought Fusion 360. You can also do it locally as well, which doesn't cost any cloud credits, and it'll use the resources on your computer. But if you do it on the cloud, you can do multiple at the same time, and it'll work in the background while you are working on Fusion. So I'll go ahead. I already ran a simulation, so I'll go ahead and show you guys that instead. So this is what the simulation would look like after you run it. You can see that the red obviously signifies that that's where it's hot. That's where it's about 75 degrees Celsius. And then it slowly spreads out. We can use our inspect tool here with surface probes to check the temperature of the fins now. And you can see it's still quite hot compared to the piping in the middle. It did help a little bit, the convection and radiation, but it didn't quite get it as cool as we wanted to. So if someone were to touch this in less than a second, it should probably burn them, unfortunately. So what we're going to do is we're going to want to modify our design a little bit and then test it again. So what we can do now is go back to our simplify workspace. We can go to the simulation model that we had, which is what when we if you guys recall, when we took away the fittings and the water, and we're gonna clone the simulation model so it keeps all the components with it. And now what we're gonna do is extend the fins out, so then it can not only get more convection, more wind passing through it, but it'll have more time to slowly lose the heat.
Yeah, so again, this is the power of having an integrated system, right? So something like ANSYS, you would have had to send out the model again, or had your designer or your engineer redo all of this work, or maybe just add a couple more fins, spend more time trying to send out that data, where instead here in Fusion, right, you're automatically just adding or extending the fins a little bit longer for your model.
Yeah, exactly. You can pretty much model in the same tool that you're using to simulate or run the simulation on. So I already actually had a simulation model created with the fins extended. So now it should allow us to have a cooler radiator in the end. So if we go here to, I already ran this result as well. If we go to the results of the finalized product with our surface probes, we can see that the temperature does significantly decrease on the ends here, as opposed to the one before, where they're all like 70 degrees Celsius. At least we're going down here to 60, 61, 67 degrees.
Yeah, for the solutions, you could also, for the drop down right there, Brian, where it's saying temperature, you can do your temperature gradient, right, your heat flux. So you have a couple other options if you want to really analyze your model a little bit deeper.
Right, and you're also able to drag this bar here in the legend. I thought this was pretty cool, where you can see, okay, where is it 340 degrees Kelvin? It would be these locations here. And once again, these are all estimations that the solver is giving you. There aren't like exact values.
Yeah, so again, going back to the thermal gradient, right? So then essentially that's showing you the temperature over the change in distance for your model. So obviously this would be a lot cooler, it would have much different results than the other one previously, right? Because you have smaller fins, so the plates are going to get hotter a little bit quicker.
Right. Also to note, before running your model, make sure your meshes are correct, or is a size that is not too big or not too small. So for example, let me go ahead and turn on the mesh for this. Now notice meshes are what is used to calculate the simulation. Is made up these little tetrahedrals here, and the more dense your mesh is, the longer your simulation will take, but usually the more accurate your results will become. If you have bigger tetrahedrals, you might get faster results, but they might not give you as accurate results. So just keep that in mind, guys. If you're getting some weird results, try messing around with the meshes located in the settings here. All right. Yeah, if you guys have any questions on this example, leave in the comment below, and we'll gladly address them at the end. But we'll go ahead and move on to our next example, which is the brake assembly here. And more specifically, we'll be focusing on the router. Now, the router, how this brake works is that when the car comes to a stop, this red caliper here clamps the brake pads, which is where my mouse is hovering over right now, and it applies friction to the rotor, and which will eventually get hot, and over time it might you might need to change your rotors because it's experiencing a lot of stress there. So let's go ahead and take a look at what we're going to be simulating. So just like the radiator from the model workspace, we'll hop over to the simulation workspace. Once again, prompted with the question, what kind of simulation we want to run. And now we're in the simulation workspace, we're going to once again work from left to right. I don't have anything else I want to simplify in this simulation. The material is what I wanted, already specified that in the model, so I'm going to leave it as same as model. For loads, first there's going to be convection occurring along in between the vanes here, which are these little panels in between the rotor here. So I'll go ahead and create a convection load for that. Once again, just like the radiator, strategically highlight just the middle part. And I'll set a convection value for that, as well as apply a heat source, which is coming from the brake pads on this face, as well as that face. And that'll be at 6,500 watts. And that's pretty much it for this thermal simulation. There's no context needing to be created. The pre-check is green, so once we hit solve, we'll get results such as this. And like the radiator, we can also check the surfaces of the temperatures here and see. So for example, if the temperature is too hot here, your brakes might slip. So this is a good test for that. And it's also a good test for the insides of where your bolts will lie. If it gets too hot there, or later we'll be testing the stress as well, then your bolts might not be as fitted as it was before. So that might lead to you might need to change your rotor later down the line. So like I said, we're going to test the stress. So unfortunately, thermal can't test everything. We need to do a combination of thermal and real life stresses as well. So what we're going to do is go back to our thermal stress here, and we're going to go ahead and clone the study. So we'll have another thermal analysis. However, if we go here to manage, we can change that to thermal stress. And now not only are we looking at the heat, but we're also going to be looking at real life stresses, real physical forces. So with this, we're going to need some constraints. And we're going to use pin constraints. There is a bolt constraint out there, but you need to have those components in here as well. We will have like if you guys are interested, message us individually and we can show you guys or talk to you guys about the bolt connectors option, but that would require the actual bolts in play as well. And that's a whole different other story. So we'll temporarily use pins for this example. So once again, I'm okay with the simplify. I'm okay with the material. I just applied my constraints. Since I cloned it, I have my convection. I have the heat being applied. Now I just need to run the simulation. Let me see if I have all my loads checked here. I'll go ahead and turn on gravity. And yeah, let's go ahead and when we do go ahead and run it, we will get a result like this. We can hop between a bunch of different tests that was run in the simulation. But let's focus on the stress on this one. So notice how if I drag my bar up here, there's stress that's occurring at near the bolt locations. So now let's create another thermal stress to enact it as if it were this car was coming to a stop and you're applying the brakes. So notice how we got this result from the thermal analysis in combination with the stress. Because if thermal alone couldn't have given us this result. So let's go back here to the one we were working on. Once again, clone the study so we don't have to keep applying the convection and the heat, the surface heat. And now we will be adding, we already have our constraints down as well. We will be adding the moments. So we'll add a structural load. We'll be adding it to this face and this face right there. And it'll be slowing down at this value here. So once again, we can go ahead and run this result either locally or on the cloud. And lastly, we'll get study number 7 here, thermal stress. So from this result, if we go to the stress here, we can see that we can see how the rotor reacted when the car comes to a stop. And if we apply our surface probes again, let's see what we get. All right. So notice how every other location, even though I selected around the same location where the bolt connector lies, it jumps up to 950 megapascals. It goes down to 650 megapascals, and it comes back up to 900 megapascals. So that's not really what we would want in a rotor, for it to be that inconsistent in terms of the stress and how much stress is being applied to the rotor. And if you look in the background here, you can see this is where the vanes are located. And notice how there's a vane located perfectly on this location, but there's not one located over here where it's has a lower stress. So what we want to do is increase the number of vanes and see if that helps distribute the stress occurring on this rotor here. So what we can do now is go to our modeling workspace, since it is the modeler as well. And we can go to the feature in which it's occurring. And instead of 15 vanes, let's go ahead and put in, let's say 20 vanes. And it'll update right there. And then when we go back to the simulation workspace, we can run this and then get a result like this. And let's see if the stress was distributed. So if I go back to my surface probes, so it's better. It's not 900 and 600 anymore. Now it's just consistently around the 600 range, 620 range. And if I move my bar here, you can see that there are more vanes that are helping to distribute that load. All right. So before we answer any questions, I just want to let you guys know about our service here. It's called Fusion Boost. It comes with an introductory call with one of our Fusion 360 experts here to help you get started with Fusion. It includes how to manage your data, use your interface, and things like that. We also have a fundamentals training webinar once a month that gives you introductory to not only sketching in Fusion, but 3D modeling as well. We also have technical assistance, which is 4 up to 1 hour sessions with Fusion 360 experts. And this allows you to use it however you want. So if for 1 hour you want to do training specifically for let's say surface modeling, you could do that. If you need help with one of your models, we can help you with that. It's all up to you guys on that. And if we don't hear from you guys after you guys get Fusion Boost, we'll also follow up with you guys to make sure we're like a kind of like a guitar coach. Yeah, I like to say.
That's a good way to put it.
Yeah, to make sure that you're using your tool. And lastly, you have access to our webinars, and we also reach out to you when we have local meetups here in SoCal. So here's the pricing for Fusion Boost. If you get Fusion 360 alone, it's $300. If you get Fusion 360 with a KETIV Boost, or a KETIV Fusion 360 and Boost, it's $499, and Fusion 360 Ultimate and Boost is $1799. So yeah, write down our emails, reach out to us, give us a call. We'd love to talk about Fusion 360 with you guys or anything about Boost. But yeah, do we have any questions?
Yeah, it looks like we have a question here from Paul asking, can't you reflect the gradient of the water as it flows through and the corresponding fin temp gradient? So unfortunately, you can't really reflect the gradient of the water as it's flowing through the pipe there. That would be more of a CFD solver, which don't quote me on this, but it looks like there's a pretty high possibility that it might get implemented into Fusion 360, right? So that's something that's been talked about in the Fusion 360 Idea Station, which is great, right? So Fusion Autodesk really listens, like I mentioned in the beginning, they really listen to their customers. And if you have an idea, or maybe you have a different workflow for how to do some of these simulations, and right, you want to see something implemented into Fusion, you can go into the Fusion 360 Idea Station and type up that idea. If you get enough votes, right, to get Autodesk's attention, then they can possibly look into implementing that into Fusion, right? But yeah, unfortunately, that would be more of a CFD solver.
All right, if we don't have any other questions, I think thank you guys for attending.
Yeah, absolutely. So again, guys, at the end of the webinar, you are going to get a